Man-made object has left our solar system. NASA is saying the Voyager 2 probe is now in a space between the stars after exiting the sun's protective bubble, which is called the heliosphere.
Voyager 2 has always been the quiet overachiever of deep space exploration. Launched in 1977 alongside Voyager 1, it rode a rare planetary alignment that allowed a sweeping tour of the outer solar system. Across decades, its cameras and instruments turned distant dots into textured worlds, and it remains the only spacecraft to have visited Jupiter, Saturn, Uranus, and Neptune. When people frame a moment as NASA revealing Voyager 2's shocking last pictures after 47 years in space, the excitement is really about the enduring power of a visual archive that can still feel fresh, even though the images themselves trace back to the mission's great planetary encounters. Before we start, smash the like and subscribe buttons for more updates. The phrase "last pictures" can sound like a sudden cinematic finale, but Voyager 2's imaging story is better understood as a sequence of chapters that rose to a peak during its giant planet flybys. The most dramatic images were captured between 1979 and 1989, when the probe swept past the four giants and their major satellites. Those photographs were the climax of a carefully choreographed grand tour, executed with 1970s hardware, tight power margins, and data rates that would be considered modest today. Yet the images still feel bold and modern because they depict environments so alien, so richly structured, that our brains keep returning to them like a mystery we are not done solving. To appreciate why any newly highlighted or newly processed Voyager 2 images might feel startling in the present, it helps to remember what we did not know before the flybys. Jupiter's atmosphere was essentially a telescopic impression, with the Great Red Spot famous but not fully understood. Saturn's rings were majestic from Earth but still a blurred symphony without close-up instrumentation. Uranus and Neptune were the least characterized major planets, with basic questions unresolved about their atmospheres, ring architectures, and magnetic fields. Voyager 2 arrived at each target carrying the power of proximity, the single factor that can turn speculation into observation. At Jupiter, Voyager 2 deepened the narrative that Voyager 1 had begun by expanding time coverage and shifting the viewing geometry of key atmospheric features. The planet's storm systems and shimmering cloud bands revealed an atmosphere ruled by powerful jet streams and long-lived vortices. The images reinforce the idea that gas giants are not passive spheres, but dynamic heat engines. Weather on Jupiter is a visible expression of deep internal energy interacting with rapid rotation, and Voyager 2's photographs helped solidify that interpretation in a way that later missions could refine rather than reinvent. Saturn delivered a different kind of shock, one rooted in complexity rather than raw turbulence. Voyager 2's images of the ring system presented a layered, sculpted environment where gravity and orbital resonance produced delicate waves, gaps, and braided features. The rings stopped looking like a simple set of luminous bands and started looking like a physical laboratory. That leap matters beyond Saturn itself. Ring physics overlaps with the same gravitational principles that shape disks around young stars, so these images quietly influence how scientists think about the earliest phases of planet formation elsewhere in the galaxy. The Saturn encounter also highlighted the choreography between rings and moons. The interplay of small satellites and ring particles showed how modest bodies can impose order on enormous systems through repeated gravitational nudges. Concepts like shepherding, resonant gaps, and wave propagation were not just theoretical abstractions anymore. They were visible. When modern audiences revisit these images, even without a new flyby, they are seeing the origins of a scientific language that still powers contemporary research. Uranus in 1986 was a reminder that the solar system still had the capacity to surprise in fundamental ways. In ordinary visible light, Uranus appeared reserved and almost featureless. But Voyager 2's broader observations revealed a planet with an extreme axial tilt and a magnetic field oddly offset and misaligned relative to its spin. That geometry hinted at a unique internal structure and unusual convective patterns. The images of Uranus's rings and moons added to the sense of a system that had been quietly evolving under rules that differed from the better-known paradigms of Jupiter and Saturn. Neptune in 1989 was arguably the most emotionally and scientifically resonant chapter of the imaging saga. Voyager 2 approached the last unvisited giant planet and returned pictures that presented a world unexpectedly alive with weather. A large dark storm, fast-moving cloud features, and bright streaks of high-altitude haze suggested atmospheric dynamics that rival the drama of Jupiter despite far weaker sunlight. The implication was immediate and profound. Internal heat and atmospheric circulation can dominate a planet's visible behavior even when the sun offers only a faint push. In a single set of images, Neptune became a case study in how planetary climates can be powered from within. Triton, Neptune's largest moon, amplified the sense of discovery. Voyager 2's images hinted at a young surface in places, complex terrains of exotic ices, and possible active plumes. Triton is widely discussed as a captured object from the distant outer reservoirs of the solar system, and its appearance linked the story of classical moons to the story of the Kuiper Belt. The implication is powerful because it suggests that the outer solar system is not a neat, compartmentalized arrangement of worlds, but a dynamic history of migration, capture, and transformation. When people describe Voyager 2's last pictures, they are usually pointing to the fact that Neptune was the final planetary target of the Grand Tour. After that encounter, operational priorities gradually shifted away from close-up imaging toward the physics of the outer heliosphere. Power constraints and the need to preserve essential instruments narrowed what could be run. This transition is not a tragic endpoint, but a strategic pivot, yet it does make the planetary image archive feel finite and precious. In practical terms, we know we will not get another set of Voyager 2 planetary portraits. That knowledge adds weight to every reintroduced frame. The notion of a reveal after so many years also aligns with how spacecraft images evolved through processing. Space images are not solely products of their cameras. They are products of calibration models, assembly techniques, and the interpretive frameworks used to turn raw data into coherent scenes. Advances in image enhancement, noise reduction, and multi-frame alignment can clarify faint structures or subtle atmospheric features. When decades-old datasets are revisited with newer tools, details that once hid in the background can rise into view, giving the impression that the spacecraft has spoken again in a clearer voice. This is especially meaningful for a mission that operated at the limits of distance and communication. Voyager 2 had to transmit data across billions of kilometers, which demanded careful choices about resolution, coverage, and priority. Some images were constrained by the operational realities of their era. Modern processing can unify color, stabilize mosaics, and improve the readability of faint ring features or cloud layers. The pictures may be the same photographs in a historical sense, yet they can become more legible scientific evidence in a modern one. The scientific implications of revisiting this imagery are substantial. The ring systems across the giant planets collectively broadened our understanding of how rings form, evolve, and persist. Jupiter's faint rings demonstrated that rings are not exclusive to Saturn. Saturn's intricate architecture revealed active interactions with moons and resonances at multiple scales. Uranus's narrow, dark rings challenged assumptions about ring brightness and stability. Neptune's ring arcs suggested that ring material can behave in surprisingly localized and dynamic ways. Across these worlds, Voyager 2 provided a comparative dataset that still shapes theory. The moons photographed by Voyager 2 have an equally long scientific shadow. At Jupiter and Saturn, the early close-ups helped frame the idea that moons can be geologically diverse, with surfaces shaped by tidal heating, impacts, and complex compositional histories. At Uranus and Neptune, Voyager 2 remains the primary close-range observer. Several of those moons have not been revisited, meaning that these images are not merely historical trophies, but the best available windows into their surface processes, crater records, and possible internal evolution. A particularly important implication of renewed attention to the archive is the growing strategic case for new missions to the ice giants. Uranus and Neptune are now recognized as key missing chapters in our understanding of planetary system architecture. A large fraction of known exoplanets appear to fall into size and mass ranges that make them broadly analogous to these worlds. Voyager 2 provided only a first draft of their atmospheric chemistry, internal structure, and magnetospheric behavior. When scientists argue for future orbiters or probes, they often anchor their case in the tantalizing incompleteness of what Voyager 2 showed in passing. Voyager 2's images also reinforce the value of comparative planetology. Seeing the giant planets through one mission allows patterns to emerge across atmospheric behavior, ring morphology, and moon populations. Jupiter and Saturn demonstrate what massive gas giants can do with abundant hydrogen and helium and strong internal heat flows. Uranus and Neptune show how different compositions and thermal histories produce different magnetic architectures and atmospheric expressions. This comparative perspective, born from a mission that was never guaranteed to succeed at every step, remains one of the most powerful scientific gifts of the Voyager era. There's a quietly profound engineering lesson embedded in the durability of these images. Voyager 2's cameras were designed for an environment of uncertainty and distance using technology from a pre-modern digital era. The fact that their output can still be meaningfully reinterpreted decades later is a testament to robust design and disciplined calibration. It also underscores an important principle for current mission planners. The most impactful spacecraft are those built not only to answer today's questions, but also to preserve data quality well enough to answer tomorrow's questions that we cannot yet articulate. The cultural significance of bringing these images forward again is hard to separate from the science. Voyager 2 symbolizes endurance in an age of fast obsolescence. Most tools we use daily are replaced in years, sometimes months. The long arc of Voyager 2 encourages the public to think of exploration as a multi-generational project. The pictures become shared memory and shared proof that scientific ambition can be translated into hardware that outlives its creators and still serves the collective imagination. The emotional power of the images also arises from how they shaped the public's mental map of the solar system. For many people, the canonical look of Jupiter's turbulent bands, Saturn's intricate rings, and Neptune's deep blue aura comes from Voyager-era photography. When those frames are celebrated again, it can feel like a rediscovery of the solar system itself. That sense of rediscovery is not just sentimental. Public awe helps sustain the political and financial oxygen that future missions require. Even allowing for headline exaggeration, there are genuine surprises in the Voyager 2 archive that still challenge. Intuition. Neptune's vigorous weather under low solar input, Uranus's unusual magnetic configuration, the intricate sculpting of rings by small moons, and the diverse resurfacing patterns of icy satellites all forced planetary scientists to expand their models. Those expansions still echo through modern interpretations of both our solar system and the broader catalog of exoplanets. In research settings, the images remain anchor points for theories built on limited observational opportunities. When a dataset is based on a single flyby, every refinement in calibration or contextual interpretation can adjust assumptions about surface age, compositional gradients, or atmospheric circulation. Revisiting older imagery is not nostalgia. It is one of the most efficient ways to extract more science from a mission already flown. The images are a return on investment that keeps paying, not because the spacecraft is still taking planetary photos, but because we are still learning how to read what it already gave us. The renewed spotlight on Voyager 2's last planetary pictures also nudges us to view the outer solar system as a connected environment, rather than a set of isolated attractions. The planets, rings, moons, and charged particle regions interact across scales. The images provide context for understanding how magnetospheres sculpt ring particles, how gravitational resonances reorganize material, and how moons can influence their local systems through subtle but persistent forces. Even when imagery is the starting point, it leads to a much wider scientific web. Legacy datasets like Voyager 2's also carry educational implications. They are ideal training grounds for students and early career researchers who want to practice image analysis and planetary interpretation with real constraints and real uncertainties. Techniques from modern computation can be applied to these images, generating new mosaics, improved feature detection, or comparative frameworks that align Voyager-era observations with contemporary simulations. In this way, the last pictures remain an active classroom and an active laboratory. Taken together, the event of highlighting Voyager 2's last images after nearly 5 decades reads as a statement about continuity. It affirms that discovery is not always a single explosive moment. Sometimes it is a long dialogue between observation and interpretation. Old images become new evidence when our tools, theories, and questions evolve. The outer planets are still puzzling, still rich in phenomena we cannot fully explain, and still foundational for understanding how planetary systems are built. Voyager 2 also quietly reframes our place in the cosmos by showing that planetary diversity is the rule rather than the exception. The outer solar system is filled with extremes that stretch the imagination. Storms that outlive human careers, rings that behave like miniature astrophysical disks, moons that hint at complex internal histories, and magnetic fields that refuse neat alignment. This diversity matters because it becomes the interpretive lens through which we view the thousands of exoplanets now known. There is another layer to why these images still hit with such force when they are brought back into public focus. They represent a specific moment when humanity's reach briefly exceeded its own expectations. The visual record from those distant flybys is not just evidence of what was there. It is evidence of what our planning, patience, and willingness to gamble on a bold trajectory made possible. The shock people feel is as much about the improbable elegance of that success as it is about the sights themselves. The renewed attention also highlights how rare true first looks are in planetary science. A first encounter compresses centuries of imagination into hours of data return. Before a spacecraft arrives, even the best telescopes leave room for ambiguity. After the flyby, the planet is no longer a mythic sphere with approximate traits. It becomes a place with identifiable structures, boundaries, colors, moods, and in some cases, mysteries that deepen rather than resolve. The fact that the outermost targets were still largely unknown at the time made the resulting images feel like a sudden expansion of the solar system's personality. The pictures are also a reminder that scale is not just a number in space exploration, it is a visceral experience. Outer planet imagery is saturated with the tension between enormous forces and delicate structures. You see vast atmospheres shaped by rotating energy and deep chemical layers, and then you see thin rings that behave like lace under relentless gravitational stress. That contrast is a recurring theme in the Voyager 2 dataset. It invites a broader scientific curiosity about how complexity emerges in environments that are, by human standards, extremely cold, extremely distant, and extremely large. One implication that continues to grow in relevance is the way these images influence the search for habitable environments in unexpected places. Even when the pictures do not directly show subsurface oceans or active chemistry, they contribute to a larger framework. Worlds are not defined only by sunlight. The outer solar system taught researchers to take internal heating seriously, to recognize that tidal forces and radiogenic energy can create pockets of activity where naive models would predict inactivity. The imagery helped normalize the idea that planetary and satellite liveliness can be hidden beneath surfaces or expressed in subtle atmospheric hints. That conceptual shift is now foundational for interpreting icy moons across the solar system. When later missions studied other satellites in more detail, the expectations set by the Voyager era shaped what scientists looked for and how they prioritized targets. The images from the Grand Tour implicitly argued that small bodies could be interesting on their own terms, not merely as accessories to the planets they orbit. That recalibration of curiosity is one of the most consequential legacies of the visual archive. Another fresh angle on the significance of the last planetary pictures is how they interact with modern simulation science. Today's atmospheric models, ring dynamics codes, and interior structure hypotheses often depend on sparse anchor points. Voyager 2 supplied many of those anchors for the ice giant systems. When researchers test a model of high-altitude haze behavior or ring confinement, they are frequently validating their predictions against patterns first documented in those images. The practical implication is that a single flyby can keep shaping first-order theory decades later. The pictures also serve as benchmarks for instrumentation progress. Modern cameras on newer missions can capture higher resolution, better low-light performance, and richer spectral detail. But comparing them to older data is not simply a contest of quality. It is a study in how scientific questions evolve. The Voyager 2 images show what was prioritized when the unknowns were broad and urgent. Contemporary instruments often aim at narrower, deeper puzzles. The contrast underscores that exploration is sequential. The first pass defines the map, the next passes write the footnotes. The public revival of these frames further draws attention to the invisible infrastructure behind them. Deep space images are not only the product of a spacecraft's camera, but also of ground systems capable of receiving faint signals and reconstructing them faithfully. The existence of a coherent image archive across such distances reflects the long-standing commitment to communication networks that can support low data rates and extended missions. This matters for future plans that might involve probes operating far from the Sun with limited power and constrained transmission. There is also an archival implication that often goes underappreciated. Space images are historical artifacts, but they are also living scientific objects. Maintaining their usability requires careful attention to metadata, calibration files, and documentation of how the original instruments behaved. When older images are reprocessed, the reliability of the result depends on how well the mission preserved the context of its own data. Voyager 2's continuing impact demonstrates the value of disciplined data stewardship from the earliest days of a mission. The emotional charge of these last pictures is amplified by the way they compress time. Each frame is a snapshot of a world at a specific season and geometry that may not repeat in the same way for decades. Giant planet atmospheres can change dramatically on timescales of years. Ring brightness and structure can be influenced by subtle shifts in particle populations or impacts. Moons can be resurfaced by events that are not predictable. The images thus become time capsules for planetary climates, offering reference points that let scientists and the public imagine what may have changed since. This time capsule quality becomes a bridge between generations of researchers and enthusiasts. A student looking at an image of a distant moon today is interacting with the same light patterns that earlier scientists pored over when the data was new. The implication is a kind of scientific continuity that is rare in fields driven by both technological leaps and short academic cycles. Voyager 2's archive allows for a shared baseline of wonder and analysis. The role of aesthetic power should not be underestimated either. The outer solar system is inherently abstract to most people. Distances are too large to intuit, and physical conditions are too extreme to imagine comfortably. Images translate abstraction into something emotionally legible. When those pictures are resurfaced in a modern media ecosystem, they can punch through information fatigue in a way that raw numbers or charts often cannot. The beauty of the data becomes a channel for scientific literacy. There is also a policy dimension embedded in the public fascination. When a mission's images remain culturally resonant for decades, they become evidence that long-horizon investments can deliver returns beyond immediate scientific papers. This matters in an era when budgets and priorities are constantly renegotiated. The implied argument of Voyager 2's visual legacy is that patient exploration creates durable value, not just discoveries, but narratives that help societies justify future exploration with confidence. The revived emphasis on the final planetary images also encourages reflection on mission risk and ambition. The outer solar system is not forgiving. Communication delays, harsh radiation environments near certain targets, and narrow windows for observation make every encounter a high-stakes choreography. The images are, in that sense, records of navigational bravery and operational precision. Their survival and clarity demonstrate what can be achieved when engineering and scientific goals are aligned under a coherent, daring plan. A more subtle implication concerns the psychology of exploration. Missions like Voyager 2 recalibrate what feels possible. After a successful grand tour, new proposals can be more audacious because a precedent has been set. That cultural effect is tangible in the way later mission concepts have imagined complex trajectories, multi-target campaigns, and long-lived operations. The memory of successful risk-taking becomes part of the institutional imagination. The images also feed into the broader story of how we define frontiers. The outer planets are not just far away, they represent the edge of the solar system's main architectural narrative. A close look at them changes our understanding of how the system is put together. The implication extends to planet formation theories, how building blocks migrated, how compositions diverged, and how early dynamics shaped the final arrangement of worlds. Visual evidence, even when it is not directly compositional, adds texture and constraints to these models. Another angle worth emphasizing is how these pictures shape the language of popular science. The metaphors we use for rings, storms, and icy terrains often originate in the imagery of early reconnaissance missions. The way educators, filmmakers, and communicators depict alien landscapes draws heavily on the aesthetic vocabulary established by the outer planet flybys. When those images are reintroduced to new audiences, they refresh the cultural toolkit for imagining the non-earthly. These photographs also invite a careful kind of humility. The outer solar system is a reminder that nature does not optimize itself for our understanding. Some of the most striking features found in the images do not fit neatly into simplified categories. The planets and moons show behaviors that require cross-disciplinary thinking. Fluid dynamics, electromagnetism, chemistry under exotic temperatures, and the slow artistry of orbital mechanics. That complexity is an implicit invitation to keep expanding scientific collaboration. In the same breath, Voyager 2's lasting visual impact underscores how powerful limited data can be when it arrives at exactly the right moment in scientific history. The late 20th century was ripe for a transformation in planetary science. The frameworks existed, but they needed close-up reality checks. The images provided those checks. In doing so, they helped shift the study of planets from speculative astronomy into a mature, evidence-rich discipline with comparative methods and robust predictive models. The shocking framing also aligns with a modern reevaluation of what counts as a milestone. Not every milestone has to be a fresh observation. Sometimes the milestone is a renewed communal recognition of what was achieved and what it still means. When a mission's most iconic images are treated as news again, it suggests that their interpretive value or emotional resonance is still expanding. The event becomes less about novelty and more about perspective. There is, too, an implication for how we talk about the future of deep space imaging. The outer solar system is a prime candidate for next-generation approaches, orbiters that can watch weather evolve over years, atmospheric probes that can connect cloud-top imagery to chemical profiles, and high-resolution surveys of moons that were only briefly glimpsed. The Voyager 2 images act like opening sentences that make the rest of the story feel urgently worth writing. In that sense, the pictures function as a kind of scientific promise. They imply that a richer atlas of the distant solar system is achievable. They show the reward of proximity and remind decision-makers that even a single pass can transform a field. The emotional logic is clear. If brief encounters could reveal such variety and beauty, sustained missions could reshape our understanding even more profoundly. The enduring fascination also intersects with the expanding exoplanet era in a more nuanced way than simple analogy. It is not only that Uranus and Neptune-like planets appear common elsewhere, it is that the Voyager 2 images remind us how deceptive first impressions can be. A planet that looks calm can hide strange internal structures. A world far from its star can still be meteorologically dramatic. A moon can carry a history that hints at migration and capture. These lessons encourage caution and curiosity as astronomers interpret faint signals from distant systems. Finally, the renewed celebration of Voyager 2's last planetary images offers a quiet statement about meaning in exploration. Spacecraft photographs are among the rare human artifacts that depict places no human has ever seen directly and may not see again for a long time. They are proof that our species can extend perception across unimaginable distances. The implication is not only scientific advancement, but a widening of human identity. We become, in a small but real way, a civilization capable of remembering landscapes beyond our home world. So when these images are presented as a revelation, after nearly half a century, the impact is not just rooted in what the camera captured, it's rooted in what the images continue to enable. They still foster new hypotheses, justify new missions, inspire new generations, and remind the wider public that the solar system is not a finished story. The last pictures from that historic sweep remain a living threshold, a place where past daring and future ambition meet in the same luminous frames. Another dimension of the moment is how these images quietly demonstrate the power of restraint. Voyager 2 didn't have the luxury of endless retakes or sprawling storage. Each sequence reflected trade-offs between ambition and survival, between capturing a broader panorama and protecting the core systems needed to complete the next encounter. That constraint shaped a visual style that feels almost curated, as if the mission were selecting the most meaningful glimpses of each world rather than attempting to exhaust them. There's also something uniquely human about how the images were designed to be comprehensible across distance and time. The framing choices, the emphasis on recognizable horizons, the patient assembly of mosaics, these are not just technical decisions. They are acts of translation, turning alien environments into scenes the human mind can hold on to. The result is a kind of interplanetary literacy, where a distant cloud layer or a faint ring arc becomes part of our shared visual vocabulary. Seen this way, the legacy of Voyager 2's last planetary views extends beyond discovery into continuity of meaning. The images don't just tell us what those places look like. They show how far careful attention can travel, how a finite set of photons captured long ago can still reshape imagination now, and how exploration can remain vivid even when the camera has long since turned away. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Voyager 2's final shocking images revealed? We want to hear from you. Thank you for watching and see you next time.